So now let's discuss the simple linear regression. What is it? How the model looks like and all that kind of things. Well, first of all, let's start with a general definition of univariate or simple regression, right? So in this case, you have only one y variable and only x variable. And y depends on x by applying a certain function. So we can say that y is a function of x, right? And in this case, if f is linear, then the regression is also linear. But if f is nonlinear, then the regression is also nonlinear. So that's the simple idea. And these are some examples of such functions. For example, this is a linear regression. You can see y. It's a linear combination of x plus error. We always have these residuals. You remember from ANOVA as well. So this is what we model. So this is the explain it part. This is what we explain. And this is the residuals. Okay, and this is the residual. So this is a linear regression. And then if you think about nonlinear regression, the simplest case can be a polynomial regression, right? So we have a polynomial of degree 2. So you can see that this is the linear part. This is the same as here, but then you add this curvature, right? So the quadratic term, so to speak. So this is a polynomial regression, and of course you have the residuals as well. You can also think about polynomial of higher degree, for example, cubic polynomial. So you add also a cubic term, or polynomial of higher degree. So you can model actually any curve with using polynomials. Okay. So the main goal in all these cases is to find the coefficients. So you have b0, b1, b2 in all these polynomial regression functions. And then you need to find these coefficients. You need to turn them to numbers in order to make the best fit possible. And this is just an illustration. So in this case, you have a linear regression. You can see that we have a straight line. So this is the regression model, right? It's just a straight line, b0 plus b1x. And then you can see that indeed points follow this linear regression trend. But in this case, for example, the line, the model is not linear, right? So it means that it's either polynomial or maybe exponential or maybe any other function. But you can clearly see that it has a curvature, it's bent. And in this case, it also fits the points very well. Like in t-test, like in ANOVA, we also have this population versus sample problem, meaning that we have the real coefficients that are valid for the whole population, right? If you have the access to the whole population and fit all population points with regression model, you will get this true real coefficients, the expected, theoretical expected coefficients. But in fact, you take a random sample, which is of size n, and this n is much smaller than the population size, and you estimate your sampling statistics. So the regression coefficients you estimate for your sample are sample statistics. And the same idea as, for example, you remember m versus mu, right? So it means that you can also find this relationship between m and mu. You can find how far coefficients of b can go from the parameters beta. You can make confidence intervals. You can make tests for different statistical tests and all that kind of things. That's what we are going to talk also about in this learning sequence. So we'll call parameters as for the population, and then these coefficients, we'll call them either coefficients or estimates. So it means it's estimates for our parameters, sampling estimates of our parameters. And then, as you already know, the regression model, the linear model, consists of two parameters, b0 and b1. You can see that I have y with a little p here, and I don't have the term, the residual term, right? So I will explain this a little bit later, but p means predicted. Okay, so it's a theoretically predicted values. Nevertheless, so the regression model looks like this. So it's a straight line. And the meaning of coefficients is follows. So first of all, the b0, you can see what happens, what meaning of the b0. It's what happens if x is equal to 0, right? So yp will be equal to b0 if x equal, yp equal to b0 if x is equal to 0, right? So it means it's an intercept. So this is exactly, this part is x equal to 0. And this is what y will be equal to if x is equal to 0, or we call it intercept because it's exactly where the line crosses the y-axis, right? So this is intercept. In many cases, it has a direct meaning, but we will discuss the practical cases later. And the second regression coefficient, b1, it's a slope of this line. You remember what is a slope? Slope is a tangent of an angle, right? So you can think about an angle like this. So this is an angle between the line and the x-axis. And the tangent, you remember, we compute tangent as ratio of this side of this triangle, right? And this side of this triangle. So this is what we call the tangent. And that's exactly the slope. So the ratio between these two cathetes, so to speak, it's a slope. And then you can see slope has a very important meaning. So if you set delta x equal to 1, then delta y will be exactly equal to b1, right? So it means that what happens to y if you change x by 1, by, for example, 1 centimeter, or by 1 kilogram, or by 1 anything you measure x in. So if you change your x variable by 1, your y variable will change by b1. And that's why we call it effect, right? Because that's exactly what happens to y if you change x by 1 unit. Okay. So these are the coefficients. Now, you can see that in this case, I already get back to my notation with y. It's not yp, right? So it's a full model with residuals. So this is dependent variable. This is what you measure. This is the independent variable, also measure it. This is the intercept, and this is the slope. And this is the random error. So it means that the measured values and the predicted values, remember these are predicted values, right? They are not the same. You always have random error. And then let's get back to these two notations that I used so far. So you can see that this is y, it's a real reference values that you measure. And here you have residuals. And here yp, it's what you predict. Not what you measure, but what you predict, right? And the idea, now you can define clearly what is error of prediction. It's a simple difference between these two, right? So E is a simple difference between the real measured y value and the predicted one. Because the real y value, it's very rarely, it depends only on x. It depends on many also random factors, right? So you always have a y different from predicted values, from yp. Even if you have a linear trend, physically justified linear trend, for example, between two variables, you always y is different from yp, and that's what we call error of prediction. Okay. And now let me show you an example. In this case, I use people data. This is 32 persons. This is age of this persons in year. This is income of this persons in Europe a year. And then you can see that although the points are pretty much scattered, you can clearly see a linear trend, and we can make a fit. We don't know yet how to make the fit, but I made this fit for you. So this is my model. It says if you take age of person, multiply to 830, and subtract 1156, you will get an average salary of this person of that age. Okay. So now you can actually use this model, right? So let's take an age, for example, 33 years, right? And then we can ask a single person of 33 years old, randomly pick it, what's your salary? And then that's the number we get. So this is the real salary of a particular person of 33 years old from our sample. Now we can also put this age to this model and make a prediction, right? So this is the predicted value. This is what model thinks the salary should be. So the difference, the distance between these 2 points, is exactly error of prediction. This is just an illustration. In this case, I use 34 years as an x. And this is the real salaries that I have in my data set, 32,000 krona. Now I put 34 years to this expression, to the model, right? So you can see that 34 times 830 minus 1156, this is the predicted salary. So this is the position of this red point, 27 or 64. And this is the real, 32,000. So the difference between the real salary and the predicted salary, that's our error of prediction. So this is how much model cannot explain, because salary also depends on many other factors. But that's the difference between the real salary and the predicted salary. And this error of prediction is the most important parameter that we also need to use in order to find the best position of this model, right? So the best orientation of this line. And that's actually what we are going to talk in the next video, how to find this line. How to find the line that fits your points best.